Hi, everyone, and welcome to section 9.4, which deals with rare events, the sample, the decision, and conclusion. Okay, so when you're working on a hypothesis test or a test of significance, there are a lot of things to consider. So let's suppose you think about let's suppose you make an assumption, a null hypothesis assumption about the property, about a property of the population. Okay, then let's say you gather data. If the sample has properties that would be unlikely to occur if the assumption was true, then you might think that your assumption is probably wrong, since the data appears to contradict your assumption. So let's say, for example, that you and your friend Conchita are at a party. There's a party game where everyone puts on a blindfold and grabs a prize from a basket. So let's say there's 200 plastic bubbles in the basket and only one of them contains a $100 bill. So pretty exciting. Okay, so so let's say the assumption is that only one of them contains a $100 bill. Okay, so that's let's say the probability of getting that bill is 1 out of 200, right? Because there's 200 total. So that's really, it's 0.005, which is 0.5%. So let's say Conchita goes first and her bubble contains the $100 bill. So like right off the bat, the first person that goes gets the $100. That's very unlikely. So what we do is we hope that what they told us was wrong and that there's more than just one $100 bill in the bucket. So basically, a rare event has occurred, Conchita getting the $100, that's the rare event. So that makes us doubt the assumption that there's only one $100 bill in the basket. So that's kind of like how the null hypothesis works. So, so what we do is, but how do we quantify this, right? We use the sample data to calculate the actual probability of getting the test result. So it's a p-value, yeah? So p-value is the probability that if, right? So this is a big if. So meaning that we assume that the null hypothesis is true. So from the get-go, we assume that it's true. And then we say, okay, let me see if this is true, what's the probability of me getting this certain result, okay? The probability that if a null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the sample. Okay, so if you get a large p-value calculated from the data, it kind of indicates that you shouldn't reject the null hypothesis. So, so using a graph, the hypothesis is easier to perform with a graph because we can see the problem more clearly. Okay, so let's do an example, super fun example, okay? Suppose a baker claims that his bread height is more than 15 centimeters on the average. So right away, you should have like a little warning red sign like, hello, it said average. So that should kind of start you thinking about, okay, well, what symbol represents average? That's that weird looking mu thing, right? This little this thing right here. Okay, so the baker's claim is that his bread is higher than 15 centimeters on the average. And a lot of his customers do not believe him. So to persuade his customers that he is right, the baker decides to do a hypothesis test. So this is how he does it. He bakes 10 loaves of bread. The mean height of the sample loaves is 17 centimeters. The baker knows from baking hundreds of loaves of bread that the standard deviation for the height is 0.5 and that the distribution of heights is normal. Okay, so right away, we can kind of start seeing, look, we're trying to show people that his bread, the average of the bread really is greater than 15. So that's the alternative hypothesis. This actually should be an A right here. So make sure that in your notes that this is an A. Okay, so when the null would be the contradictory statement to this. Well, the bread is less than or equal to 15 centimeters, okay? So what he does in his test, he uses what's his sample size, right? The sample size is 10, right? So n equals 10. So when you read this, you should be writing down n equals 10 Mu is 15, right? Mu is greater than 15 for alternative hypothesis. Null is less than or equal to 15. Okay, fine. Then the mean height of the sample lobes is 17 centimeters. So we already know that the mean height, x bar, is equal to 17 centimeters. That's also given to us. The baker knows from baking hundreds of loaves of bread that the standard deviation for the height is 0.5 centimeters and the distribution of heights is normal. So the standard deviation is known, right? 0.5 centimeters, sigma equals 0.5 centimeters, and we know that the distribution is normal, and we're talking about sample mean, so the standard deviation is going to be sigma over square root of n. So the standard deviation in this case is 0.16. Okay, let's suppose that the null is true, that the lobes are no more than 15. So the mean height of the lobes is less than 15 or equal to 15. Then we ask ourselves this following question. From the sample, from the data, is this height unexpectedly large? Is this a random occurrence? Like, is this a chance? Like, really, what's the probability of us getting this height? Okay, so we're basically asking the question, how unlikely the sample mean would be if the null hypothesis were true? And the graph shows how far out the sample mean is on the normal curve. So the p-value is the probability that if we were to take other samples, any other sample mean would fall out at least as far out as 17 centimeters. So another way to think about it is the p-value is the probability that a sample mean is the same or greater than 17 centimeters when the population mean is in fact 15. So remember, population mean, you use the symbol mu, and sample mean is x bar. Okay, so here's the graph, okay? So in the end, this p-value ends up being approximately 0. It's very small. So if you have a p-value of approximately 0, it tells you that it's highly unlikely that a loaf of bread will rise no more than 15 centimeters on average, right? So we're kind of thinking and doubting that null hypothesis, yeah? So that means almost 0% of all loaves of bread would be at least as high as 17 centimeters purely by chance if the population mean height was really 15. Since the outcome of 17 centimeters, it's so unlikely, right? It's so unlikely. It means, like, what's the chances of this actually happening if this was true? It's pretty much zero chance. It's almost zero chance. So this means that the evidence is really strongly against the null hypothesis, which was that the mean height is less than or equal to 15, or at most. Remember, keyword at most. At most, when you read the word at most, it should tell you in symbols less than or equal to, okay? Okay, so we can say there is sufficient evidence to say that the true mean height of the population, for the population of the baker's loaves of bread, is greater than 15 cm. So remember, because the null and the alternative hypothesis are contradictory arguments, they're contradicting each other, if you reject one, it supports the other, right? It looks like the other is more favorable, right? If you support the null, the alternative hypothesis is looking pretty good, right? We totally rejected the null right here. The chances of it being that, of us getting that sample mean of 17 with the assumption that the mean height of bread is less than or equal to 15 is like 0, basically. So we reject the null hypothesis and we support the alternative hypothesis. And your book says it in this way: there is sufficient evidence to say the true mean height of the population of baker's loaf of bread is greater than 15. Okay, so now that we know that, what is that? How is there a specific number, or what is that? So the decision and conclusion. So a systematic way to make a decision of whether to reject or not to reject the null hypothesis is to compare the p-value and a preset or preconceived alpha, which is also called a significance level. That's why they call this also test of significance, because the alpha is the significance level. If you recall, the alpha, a preset alpha, is the probability of a type 1 error. Remember when we reject the truth, right? So it may be given to you or it may not be given to you. Okay, so here we go. So this is important right here. So I would definitely pay super close attention. when you make a decision to fail or reject the null, use these steps, okay? So if your alpha is greater than your p-value, or if your p-value is less than alpha, we reject the null, okay? We reject the null, right? So the odds of this happening are so little, they're like significant, it's significant. So he says, oh, this means that the results of the sample data are significant. Yes, okay. So another way to say it is, and then we can say there is sufficient evidence to conclude that HO or null hypothesis is an incorrect belief and that the alternative hypothesis, HA, may be correct. Okay, so it kind of supports the alternative. Now, conversely, if alpha is less than or equal to the p-value, or the p-value is greater than or equal to alpha, sorry, this is wrong right here, this is wrong, change this, please, this is a greater than, do not reject the null hypothesis, fail to reject. This means that the results of the sample data are not significant, and there is not sufficient evidence to conclude that HO is false and the alternative hypothesis may be correct. Okay, and then also, when you fail to reject HO, it doesn't necessarily mean that you should just believe it's true. It doesn't mean, like, see, it's very hard to prove something true directly, okay? So it doesn't mean necessarily that it's true. It just means that the sample data fails to cast serious doubt about the truthfulness of HO. So you weren't exactly able to prove it false, okay? So then after you decide to reject HO or do not reject or fail to reject, you make a decision, you write a thoughtful conclusion, okay? So let's do a little bit more to make sure we hit on this. Okay, so when using the p-value to evaluate a hypothesis test, this is kind of funny. Sometimes it's useful to use this device. If the p-value is low, the null must go, right? P-value is low, p-value less than alpha, yeah? If the p-value is high, the null must fly, right? So, if the p-value is less than alpha, you reject the null. If the p-value is greater than alpha, p is high, we do not reject. Okay, so let's fill in the blanks. We reject the null hypothesis when the p-value is less than the established alpha. Okay, so really remember, really somewhere, write it down, sticky note, put it on your computer, I don't know where, but just put like p-value and then less than, put your little less than alpha. Okay, so that means that the results of the data, the sample data, support the alternative hypothesis. Okay, so there is sufficient evidence to reject the null and support the alternative. All right, so when do we fail to reject the null? When the p-value is greater than the established alpha value, greater than or equal to, right? And then that means that the results of the data do not support the alternative hypothesis. Okay, so that's it for 9.4. There's your homework, and happy studying, and I will see you on the next video.